Today we shall discuss the iteration. The, literally, iteration means doing the similar things repeatedly until a predefined condition is satisfied. We shall come to this iteration process while solving roots of equation using Newton-Raphson method or doing integrations, numerical integration using say trapezoidal rule or Simpson 1/3 rule. Here we are taking the iteration. We shall describe iteration by via the solution of an infinite series. Say sin x. If we expand it in Taylor series, the series is x cubed by factorial 3 plus x to the power 5 by factorial 5 and so on and so forth, which can become written as n is equal to 0 to infinity so that ti, the ith term is minus 1 to the power I. The term starts with t0 and this is x to the power 2i plus 1 upon 2i plus 1 factorial. So that t0 is, this is positive, this is x and this is 1, and t2 where this is t1 is, this is negative, this is x to the power 3 by factorial 3, and say if we, so this is t0, this is t1, this is t2 and so on and so forth, and ti plus 1 is equal to minus 1 to the power I plus 1 x to the power 2i plus 3 divided by 2i by 3 factorial. This term can be written as minus x square by 2i plus 3 2i plus 2, so that you take the first two terms, so the next term is 2i plus I factorial and this is ti. This is the recurrence relation. So if we know t0 to be x, we know t0 to be x, then t1 by this relation is minus x square and I is 1, so this is 3 into 2 times x, this is minus x cubed by factorial 3. Now come to t2. For t2 I is 1, so minus x square, I is 1 means this is 5 into 4 into t1, so this is minus, t1 is this minus minus plus x to the power 5 factorial 5, so the terms are generated automatically. So this is a recurrence relation between these two terms. So we write this one as ti plus 1 is equal to minus x square 2i plus 3 2i plus 2 ti with t0 is equal to x. So our aim is to evaluate sin x for a given value of x with specified accuracy. That is, we shall say that the value of sin x will not alter after the 5th decimal place. Say I say that the value of sin x will not alter up to 5th decimal place. So we are to take adequate number of terms, because this 0 to infinity, you cannot take all these terms in practice. So we are to take a finite number of terms, so that in reality this infinite sum, n is equal to 0 to infinite sum, is reduced to this one, and we are to choose capital N in such a way that the addition of other terms which are left behind, that is the addition of terms n to infinity, this contribution is less than some accuracy level. In the case of alternating series, if we have that ai is greater than ai plus 1, if we have, then if we ignore tn term, then the contribution coming from n to infinite terms are less than Tn. This is a theorem in infinite series. So we shall capitalize this theorem, and we shall go on increasing the value of n, so until this situation is the condition is satisfied. The one restriction keeping that x must be in radian. This x is in radian. If we want to find out sine 30 degree, then we are to convert 30 into radian, that is the x in degree is 30.0. The corresponding x in radian is 30 into pi by 180. This conversion has to be done. Now, keeping with this in mind, we evaluate the sine function like this. First we read the value of x and the accuracy level. Value of x and accuracy level. Say accuracy level is 0.0001. So the series will calculate the sign of x, which is correct up to third decimal place. Now I is set to be 0. I is an integer, so do not put any dot. Then sum. Sum, it is a real quantity, I will assign it afterwards. And then term, first term is x. Then we check if absolute value of term is greater than equal to accuracy, then what shall we do? We will calculate the next term, that is term is first we are to calculate the factor in the denominator. The factor in the denominator is 2 times I plus 3 star 2 times I plus 2. It is integer, so we want to make the corresponding float of it, float, float. So if this number on after multiplication is 5, it will make you 5.0. So this part is calculated. Then we redefine t as minus x square times t by 10. You see this, we have executed this one. So function enters with t is equal to x, so it calculates the second term of it. Then we redefine sum is equal to sum plus term, but sum has to be initialized. We first initialize sum to be x, so that already it is x, and then it is augmented by minus x cubed by factorial 3. And then we are to take decision whether the other terms are to be taken or not. Then we replace I by I plus 1 and ask the system to go to blank statement number 1. The statement number is this: else this part will be calculated only when the absolute value of t is less than the accuracy, that is the adequate number of terms has been taken into care. Here you write x accuracy, the calculated sum that you have calculated, and sign of x. If you want, you can write I, the number of terms required. Let me once again explain the working of the game. It first reads x and assigns sum to be x and term to be x. Then it checks whether the desired accuracy level has already been achieved or not. If not, then it goes to the next term. So for going to the next term, it uses this recurrence relation. This recurrence relation has been implemented over here, and then it adds the newly calculated term to the sum, which is at the first it is x, then it is x minus x cubed by factorial 3. Now the sum is this. Now it increases I by 1. So initially I was 0, now I becomes 1. Once I becomes 1, this becomes 2 into 1 plus 3. This is 5 into 4. This is 5 into 4. Now when it comes, this is 5 into 4, that is 2. This part will be there, and it will be augmented by with a minus sign. Now the recurrence relation is minus x square by 5 into 4. This is denominator times t, and t is minus x cubed by factorial 3, which is plus x to the power 5 by factorial 5. So it accounts this term. Then it adds the term to this, so the sum is now x to the power 5 by factorial 5. Now it augments I by 1, now I will be 2, and it goes there, and it calculates the next term, and this part will be repeated until this condition is satisfied. So this is the iteration part. This is the iteration part. This job is being doing repeatedly until the desired condition, the predefined desired condition. Here the predefined condition is thus. Until this is satisfied, it will be done repeatedly. And this else part will come only when this condition is satisfied. Answered, that is absolute value of t becomes less than accuracy. Then the program will come here, it will write the value of x, accuracy level, the calculated sum. This is the corresponding value that you obtain from the library function. This has been written for a comparison between these two, and you can also check the number of terms required. Then this is the iteration problem. You can have other iteration problems like I am suggesting you for a few more iteration problems of this sort. We'll consider cos x, a similar thing, cos x. Again, when it is in with, you know that factorial 0 is 1 by definition. Oh, one more thing. In this earlier program, we have not used the factorial, because if we use factorial, the inaccuracy will result in, and the calculated sum will never be equal to the actual sum for large number, when large number of terms are involved. Then your task is to calculate ti plus 1, how it is related to ti e to the power x function. Then again go to the iteration relation, and you can calculate the sum. There are other things like log of 1 plus x with x here, that there is a restriction that mod x must be less than equal to the restriction is x is less than equal to 1 greater than minus 1. So this will be a complicated thing. So this is equal to x first term x minus x square by 2 plus x cube by 3 and so on. You can do this thing also. I will just say the another type of iteration which is involved in the numerical integration. Now, actually the problem of numerical integration is to evaluate a definite integral of a function f within limits a to b. So this is a to b fx dx. This has to be calculated. This is the problem of numerical integration. What one does in this is the f of x, say a to b. This is definite integral. Say the function is of this form. One divides this space into n number of strips, equi-space strips, n number of strips, n, so that x0 is equal to a and xn is equal to b. So we have one and the width of two adjacent layer is h. So one defines h is equal to b minus a upon n, and one a calculates the area under the scarf. Now for a given n, the integration has been carried out. That is, we divide the entire interval AB into a number of strips an. So this is when a to b is divided into n intervals, n equispaced, n steps of equal size. Say n is 100. we find the result. How do you know that this result is correct one? Then we are to change n. So say n was 100. Now we calculate I 100. This is one result. Then we also calculate 101, and we check what is the difference between these two. So I 100 minus I, is this less than the accuracy? If yes, it's okay. If not, then we calculate 120 and we check the if we get the desired accuracy level here, is fine. Then otherwise I will go to the next step calculation. This is also another type of iteration that we will be using during numerical integrations of function. So that's all about iteration, and by this lecture I finish the things that were included in your syllabus under the Fortran heading. From next class I shall start numerical analysis. I will start numerical analysis. First lecture will be on the root finding of roots of transcendental equations.